Okay, so let's get started. So it's a pleasure to welcome Changhoon Han from Princeton University. So Chang is an expert on cosmology, machine learning, and also galaxy evolution now. So he did his PhD at NYU with Mike Blanton, and then moved to Berkeley for a postdoc, and now he's at Princeton on another postdoc, and soon becoming faculty. So it's a pleasure to welcome him here. He will talk about his latest work on cosmology and machine learning. Tomorrow, he will give him the Galaxy Coffee as well, talking more about galaxies and ML. And he's staying until tomorrow. So if you want to chat with him, just let me know. And he has an office there, but just better to write him an email. So thank you very much, Chang. The floor is yours.
All right. Hi, everyone. My name is Changhoon Han. You can call me Chang. Thanks so much for having me here in Paradise. This talk will be in English, right? Yeah. Okay, because if it's in Spanish, you're gonna have a bad time. I'll have fun trying to say things in Spanish, but you'll certainly have a bad time. So as Mark suggested, I'll be talking about machine learning and cosmology. And in particular, my work is really centered around how we can, no, one second. Is really centered around how we can maximally extract all of the information that's in galaxy surveys, the next generation galaxy surveys, in order to inform both cosmology and astrophysics. So let me start with a brief introduction. So at this point, we've really converged onto a standard model of cosmology that we call Lambda-CDM. And according to this model, the universe began around 14 billion years ago with the Big Bang. It then entered a period of exponential expansion that we call inflation that seeded the initial density fluctuations in the primordial plasma. Then after recombination, when the photons decouple from this plasma into what we observe as the cosmic microwave background, or CMB, the baryons and the dark matter in the universe, they gravitationally form the larger structures in the universe, the stars, the galaxies that we observe. Then around 10 billion years from the Big Bang, the universe enters a period of accelerated expansion that's driven by dark energy. So in addition to providing this nice complete history of the universe, the primary reason why cosmologists have really converged onto the standard Lambda-CDM model is that it's been remarkably successful at producing a wide range of observations. And I'm showing you one example of this here. This is the temperature power spectrum of the cosmic microwave background, or CMB. I'll explain a little bit more what the power spectrum is for those of you who aren't familiar with it. And what I want to emphasize in this figure here is that the blue points that you see here are actual measurements from the Planck satellite. Meanwhile, the orange line that you see going through almost each and every one of these blue points is the prediction from Lambda-CDM. So as you can see, it's remarkably successful at reproducing the observations. So despite the successes of Lambda-CDM, however, one of the main challenges that we face is that none of the main ingredients, whether it's inflation, dark matter, or dark energy, are well understood. And in fact, we're actually at a really exciting time in cosmology because we've discovered these cosmic tensions between measurements of probes of the early universe versus the late universe. So let me explain that a little bit further. Here I'm showing you the measurements of the growth of structure parameterized using this S8 parameter. And I've labeled here in the blue measurements from the CMB that probes the early universe. So compared to these S8 measurements, what we find in probes of the late universe, so at low redshifts, are significantly lower values of S8. And at this point, we've had 3 independent weak lensing experiments, DES, HSC, and KIDS, that all find significantly lower values of S8. So in addition to this S8 tension, we also have what we call the Hubble tension. So I'm showing you again the measurements of the present day expansion rate, parameterized this H0 parameter, from experiments that probe the CMB. So these probe the early universe at high redshifts. And compared to these measurements, what we find at low redshifts are significantly higher values of H naught from supernovae and from time delay lensing. And so as the precision of our experiments have increased with time, these tensions have only increased in statistical significance. So one thing I want to emphasize here is that we have measurements of the late universe, we have measurements that probe the early universe, but there's this entire regime in between of billions of years of cosmic history where we currently do not have precise measurements of either S8 or H naught. And so one way we can fill this gap and really bridge this early to late universe measurements of both S8 and H naught is by using spectroscopic galaxy surveys like the one I'm showing you in the background here. This is the Sloan Digital Sky Survey, or SDSS. And surveys like SDSS allow us to probe both the growth history and the expansion history of the universe. And so what these surveys provide is they measure the photometry or the positions of galaxies, as well as the spectra of galaxies, which we can then use to measure the redshifts of galaxies. So then with the angular positions and the redshifts of galaxies, we can construct these detailed three-dimensional maps of galaxies like the one I'm showing you here. This is an image from SDSS from Michael Blanton, where every single point here corresponds to an actual galaxy that was observed by SDSS. So aside from just being a beautiful image, these three-dimensional galaxy distributions, they encode information about, for instance, the growth of structure from redshift space distortions. So let me explain that just a little bit here. So the redshifts that we measure of a galaxy, they have two components. First is the redshifts that come from the cosmological expansion of the universe. And then the second term is from the peculiar velocities of galaxies. So if we just had the first term, here's how we would expect the galaxy distribution to look like in real space. Now, with this second term of the peculiar velocity, this real space distribution becomes distorted in redshift space, as you can see here. So these distortions come in two broad regimes. The first one, you may have already noticed it. It's these long elongated structures pointing towards the observer down here that look like fingers of God. And this comes from the random motions of galaxies within virialized structures of halos. Then there's a more subtle effect, which you might be able to see if you focus on some of the overdense regions here. You'll notice as I go from real space to redshift space, there's a squashing along the line of sight. And this is what's called the Kaiser effect. And this comes from the coherent motions of galaxies towards large-scale structure. So as you can imagine, these effects encode information about the growth of structure. So for instance, we can more quantitatively write down the overdensity of galaxies in redshift space in terms of the overdensity of galaxies in real space, plus this additional term that depends on the growth of structure and the matter overdensity. So in practice, we don't explicitly measure the overdensity of galaxies, but instead we measure a summary statistic of the galaxy distribution, in particular, the galaxy power spectrum, which is the Fourier transform of the two-point correlation function of galaxies. So this is a measurement of the excess probability of finding galaxy pairs at some separation over a random distribution. So here's what the power spectrum actually looks like. These are measurements from SDSS at two different redshifts. So just to remind everyone here, the x-axis here, K, this is in Fourier space. So large values of K means small scale. Small values of K means large scale. So we can measure the power spectrum at different redshifts in order to then measure the growth history of the universe. So in addition to the growth of structure, the galaxy distribution also encodes information on the expansion history from the baryon acoustic oscillations. So in the primordial universe, as I mentioned earlier, the baryons and the photons, they're coupled and they propagate as spherical sound waves. Then after recombination, when the photons decouple from the plasma. The baryons are frozen in place, as you can see in this image now. So what that means is that galaxies are more likely to form on the scale of these baryon acoustic oscillations. So if we were to measure the 2-point correlation function, no worries, 2-point correlation function, then what we'd find is this excess probability of finding galaxy pairs at the physical scale of the baryon acoustic oscillations. And since this is a physical scale, like I mentioned, we can use it as a standard ruler to then measure the expansion history of the universe. So hopefully with this introduction, you have a broad idea of how we can use the 3-dimensional distributions of galaxies in order to measure both the growth and expansion histories of the universe. However, everything that I've just mentioned right now utilizes less than half of the actual information that's available in galaxy surveys. And that's because everything that I've told you so far primarily focuses on the galaxy power spectrum and on large linear scales. So this is again the power spectrum of galaxies from SDSS. And I've marked here in the black vertical dashed line the current scale limits of our analyses, which corresponds to a Kmax of around 0.2. And so current analyses focus on scales larger than this because they rely on perturbation theory to model the galaxy clustering. And so perturbation theory is only accurate on large linear scales. But there's information beyond the linear scales on smaller scales and also beyond the power spectrum alone. So here's an example that I really like to show by Emiliano Sefusati. These are 2 distributions that by eye are completely different from one another. But if you were to look at just their power spectrum, they'll be almost indistinguishable. But of course, if you look at any higher order statistics, for instance, like the bispectrum, which is the Fourier transform of the 3-point correlation, which measures the excess probability of galaxy triplets of different shapes and sizes over a random distribution, you'd immediately find that these 2 distributions are very different from one another. This is the bispectrum, this is the trispectrum. Well, that's a nice demonstration. The question still remains, how much relevant cosmological information is available beyond the power spectrum? So to answer this question, I constructed these 2 suites of simulations with collaborators, the Quixote suite of this is, I guess, a Spanish crowd, so these are pretty well named. The Quixote suite of M-body simulations and the Molino suite built on top of them. So Quixote is 82,000 full M-body simulations, which at one point was the largest publicly available suite of simulations. And Molino are galaxy catalogs built on top of these, and there's 75,000 of these. So what these 2 simulation suites provide are the ingredients to do full Fisher matrix forecasts for different cosmological summary statistics, like the bispectrum or the power spectrum. And what they allow us to do is they forecast the precision to which we can constrain the cosmological parameters. So these are the Lambda-CDM parameters. And so for those of you who are unfamiliar with these corner plots, the size of the contours here represent the forecasted precision to which we can constrain the Lambda-CDM parameters. So in blue, I'm showing you the constraints we can expect for a power spectrum only analysis. And in orange is what we can expect by including both the power spectrum and the bispectrum. So as you can clearly see, by including higher order information like the bispectrum, we dramatically improve the constraints on the Lambda-CDM parameters, and in this case, by a factor of more than 3. The other interesting thing that we find from these forecasts is, and this is a rather busy plot, but what I'm showing you here on the y-axis is the 1 sigma forecasted precision for the different cosmological parameters as a function of the maximum scale to which we analyze down to. So again, just to remind everyone, large values of Kmax means smaller scale. And I've marked in each of these panels the current scale cuts of our analysis of Kmax at 0.2. So you can see even for the power spectrum, as you go down to smaller scales, we improve the precision of our cosmological constraints. Now for the power spectrum and bispectrum, aside from being overall more precise, you can see that the improvements that we get on small scales are even larger. So what these forecasts now establish, and we've repeated this forecast for multiple different summary statistics beyond just the bispectrum. We've looked at the wavelet statistics, the skew spectra, the reconstructed power spectrum, the Mark power spectrum. And then the consensus that I've been able to establish is that there's significant cosmological information beyond the power spectrum in higher order statistics and on small nonlinear scales. So now if we were to try to extend down to the higher order and nonlinear regimes with the standard analyses, we run into a number of major challenges. So the first challenge is something that I've mentioned earlier, is that we currently rely on perturbation theory to model our galaxy clustering. And perturbation theory is really limited to large linear scales and to two-point correlations, the correlation function. So this is a figure that I like to show where I'm showing you the bispectrum as a function of scale. And then the error bars here represent the uncertainties. So on small scales, the error bars are completely dominated by the theoretical uncertainties of the perturbation theory. So as you can see at k, beyond k of 0.2, you really cannot extract any more information because you're completely dominated by your theoretical uncertainties. Another major challenge that we face, and another thing that I wanted to mention is that there's currently no analytic model based on perturbation theory that's available for many of the statistics that have been proposed and that have been shown to be very promising, such as wavelets, kth nearest neighbor, minimum spanning tree. So with perturbation theory, there'll be no way to analyze these summary statistics. So in addition to this, another challenge that we face is that observations are very messy. And this might be pretty obvious to the observers in the crowd, but not necessarily to the theorists. This is the angular distribution of actual galaxies observed by SDSS in the southern galactic cap. And you can see that there's all of these like giant holes punched in here due to bright star masking. There's these sort of claw prints from photometric completeness issues. So all of these have to be accounted for in the actual analysis of any cosmological summary statistics. And one observational systematic that I've spent a lot of time thinking about is fiber collisions. So what I'm showing you in this image here is the focal plane of SDSS. It's a big aluminum plate with a bunch of holes drilled into them that correspond to the actual positions of galaxies. And so back in the day, people used to just plug fibers directly onto these plates, load it in to observe. But because both the holes and the fibers have an actual physical size, there's a limit to how closely you can place two fibers next to each other. So as you can imagine, this means that you can only observe angular galaxy pairs that are within or outside of some angular scale. So as you can imagine, this will have an imprint on small scale galaxy clustering. So here's what the effect of fiber collisions looks like for the galaxy power spectrum, estimated with 3 different simulations in the different colors here. For reference, I've included the amplitude of cosmic variance. And what you can see is that even at k of 0.1, the effect of fiber collisions exceeds cosmic variance. So this is a very, very significant effect. And so for the power spectrum, there are correction schemes that are available, including the ones that I've worked on, but they all come with some caveats in that they're quite difficult to implement. But the bigger bottleneck is that we currently have no correction schemes that's been demonstrated to work for higher order summary statistics. So here's what I think are the major challenges that we face if we want to extract all of this additional cosmological information that's available in higher order and nonlinear regimes. So first is the modeling of the nonlinear scales, which we can't do with perturbation theory. The other is modeling higher order summary statistics beyond the power spectrum. And last is all of the observational systematics that we have to account for in our cosmological analyses. Now, of course, all of these challenges are for the standard approach, but we don't have to rely on perturbation theory in these approaches. We can instead use a simulation-based approach and address all of these. So in terms of the nonlinear regimes, while perturbation theory is limited to the linear scales, with M-body simulations, we can accurately model galaxy clustering down to much smaller scales. And in terms of higher order statistics, well, if we take a simulation-based approach, we can use any summary statistic that we can measure on the observations, as long as we consistently measure them on the simulations themselves. And lastly, in terms of the observational systematics, we already have a lot of the tools to include all of these systematics in our analyses that we currently use to validate our analysis. So we can include those into the simulations and account for all of the effects directly in the forward model. So then the only challenge that remains is how do we go from a simulation that accurately models nonlinear and higher order clustering and includes all of the systematics to the cosmological parameters that we're actually interested in. And the way we're going to do this, or to phrase this another way, is how do we infer the probability distribution of our Lambda-CDM parameters given the galaxy distribution? So the way we're going to do this is by using simulation-based inference using deep generative models. So before I go on, I want to give a brief introduction of deep generative models, and what better way to do it than asking the world's most famous generative model, ChatGPT, to explain itself. So if you ask ChatGPT, can you explain generative models? It'll tell you a generative model is a type of machine learning model that can generate new data that is similar to the data it was trained on. These models learn the underlying probability distributions of the training data. So that's really the part that I want to highlight here, because what this means is that in the back end of ChatGPT, Bard, Gemini, all of these fancy generative models is actually an algorithm that performs a density estimation. So here's an example that hopefully will give you kind of a more intuitive idea of what's going on. So here's the seminal MNIST data set. So for those of you who aren't familiar with this, these are data sets of 25 by 28 by 28 pixel handwritten digits. So one of the things that you can do is take this data set of all of these handwritten digits and then train a probability distribution to estimate the probability distribution of all of the pixels. And so then once you've trained a generative model to do this, you can sample this generative model, and then it'll produce all of these sort of handwritten looking digits. And one thing I want to emphasize here is that 28 by 28 is like 700 dimensional distribution. The MNIST data set is only tens of thousands. So this really just highlights how flexible and powerful generative models can be. So before I go on, I wanted to give a little bit more of a quantitative idea of what's happening instead of just presenting this as a black box. And the way generative models perform the density estimation is by reformulating it into an optimization problem. So the goal here is to derive the hyperparameters phi for some very flexible model Q that allows us to estimate this posterior. So one way we can do this is by minimizing the callback Liebler, the KL divergence between the true distribution and our approximation of the distribution. For those of you who aren't familiar with the KL divergence, this is the equation here, and it's a nice little illustration that highlights how this is sort of a distance metric between two probability distributions. And the nice thing about the KL divergence is that you can rewrite this integral in terms of samples drawn from the true distribution. And in this case, these samples are the simulated galaxy distributions that we can generate. So then once you have that, you can actually evaluate the KL divergence without ever having to evaluate the true distribution. And this is simply an optimization problem. So the only thing you need to perform this optimization in a tractable way is to have the model Q phi be easy to evaluate and also flexible enough that it can actually describe a high dimensional conditional distribution like the posterior that we're trying to estimate. So one model that I like to use in particular is called normalizing flows. So for those of you who aren't familiar with normalizing flows, these are a series of transformations that goes from some simple base distribution, like a multivariate Gaussian, to the target distribution that you're interested in. And these transformations are designed so that they're both invertible and differentiable, which means that you can just use change of variables to evaluate the target distribution by actually just only evaluating the simple base distribution. So with normalizing flows, you can both sample and evaluate highly complicated probability distributions, while in the back end, all you're doing is sampling a multivariate distribution. So without going into any more technical details, I should also mention that the advantage of this is that you can stack many of these transformations to increase how expressive and flexible the normalizing flows can be. So without going into any more details, let me show you some examples of normalizing flows. Here's a standard one in 2D where you can see the transformation going from a 2D Gaussian point cloud to this double moon to moon distribution. Here's some more impressive ones going from 3D Gaussian point clouds to an airplane, a chair, a car. So you can think of this as estimating the probability distribution of planes, probability distribution of chairs, or probability distributions of cars. Of course, this is not what we're interested in doing. We're interested in using normalizing flows to estimate this posterior here, the probability distribution of the Lambda-CDM parameters given the galaxy distribution. So to tackle this problem, I formed the SIMBIG collaboration, which stands for the Simulation-Based Inference of Galaxies. And so the way the SIMBIG framework works is first we generate a training data set of synthetic galaxy surveys. So we take the cosmological parameters, Lambda-CDM parameters, we generate synthetic galaxy surveys with all of the survey realism of an actual galaxy survey. We perform data compression onto the summary statistics, which is another way of saying we measure the power spectrum, we measure the bispectrum, we measure the wavelets, whatever the summary statistics we want to analyze. Then once we have this training data set of parameters and summary statistics, we train a normalizing flow to estimate the posterior of theta given the summary statistics. Then once we've trained this normalizing flow, we perform the same data compression on actual observations in the same way as we did for our synthetic galaxy surveys. And then afterwards, we plug in the summary statistics into our trained normalizing flow, and that gives us the posterior given the actual observations. So let me focus on the first part of this whole pipeline, because this is arguably the most important aspect of it, which is generating these synthetic galaxy surveys. So in our first application of SIMBIG, the target galaxy survey that we had in mind is the SDSS-3 BOSS survey in the Southern Galactic Cap. So we start off with the Quixote high-resolution M-body simulations. We then identify the virialized structures in the dark matter distribution that we call halos using Rockstar, which is a phase-space halo finder. Then afterwards, we populate the halos with galaxies using an empirical model called halo occupation distribution. And for those of you who are experts on this, we use one with all of these bells and whistles: assembly bias, velocity bias, concentration bias. I can tell you more about it in the future. And then afterwards, we apply all of the survey realism. So we apply the survey geometry, the masking, we apply the fiber collisions onto the simulated data. And in total, we construct 20,000 training simulations that spans a broad range of cosmological parameters. So here's what forward model simulations actually look like compared to the observations. So on the left is the actual SDSS survey, and on the right is the forward model simulation. And I just want to point out how we include all of these details. So you can see the bright star masking, some of the photometric systematics are all included in there. Here's another nice video of a comparison between the observations and our simulations. The color here represents redshift. And again, I want to draw your attention to all of the detailed systematics that we implemented into the simulation. And again, this is essential for us to derive unbiased cosmological constraints that account for all of these effects. I don't get to show a lot of videos, so enjoy. So now that you know how the SIMBIG framework works, I can now finally show you the results that we get when we analyze different cosmological summary statistics of galaxy clustering. So the very first galaxy clustering statistic that we applied this to was the nonlinear power spectrum. So just to remind everyone, I mentioned earlier that standard analyses using perturbation theory, they go down to Kmax of 0.2. But because we use a simulation-based approach, we can go down to significantly smaller scales, down to Kmax of 0.5. So here's the full posterior that we derive for the nonlinear power spectrum. The top set here are the Lambda-CDM parameters, and all of these are, for the purposes of cosmology, nuisance parameters, but they actually say something about galaxies and their populations. So focusing on primarily the parameters that determine the growth of structure, what we find when we compare to the standard perturbation theory approach in orange, so this is from Misha Ivanov's effective field theory, is that because we're able to extract information on small nonlinear scales, we significantly improve the constraints that we get on sigma 8. Now, of course, this is just the nonlinear scales. We're still not utilizing higher order statistics. So the next summary statistic that we apply SIMBIG to is the nonlinear galaxy bispectrum. So again, this is the 3-point correlation function. This measures the excess probability of galaxy triplets. And so what we find when we analyze the bispectrum is that because we extract information, both higher order and nonlinear information, we can improve both omega matter and sigma 8 much more than with the standard power spectrum analysis alone. So in addition to the bispectrum, we've also tried another summary statistic that was pretty fun. This is work led by Liam Parker, who was a student working with me at Princeton, and Pablo Lemos, who's in Mila. And so what we tried is we trained a convolutional neural network to compress the galaxy field. So what we did is we took the full galaxy survey, and then we trained a convolutional neural network to construct summary statistics that are maximally informative of the Lambda-CDM cosmological parameters. So you can think of this as an attempt to extract all of the relevant information, not just in the 2-point and the 3-point, but also the 4-point, 5-point, all of the higher endpoint functions sort of in one go. And so what we find when we do this is consistent improvements as the bispectrum. And you can see that we significantly improve the constraints over the standard power spectrum analyses. So at this point, in addition to the ones that I've showed you, we've also applied this to the wavelet scattering transforms, to the skew spectra, and to the Mark power spectra. Oh, that paper is actually out. And we're also working now on applying this to voids. We also have another a paper where we're training graph neural networks to compress the galaxy field rather than convolutional neural networks. And all of this work will be coming soon. So going back to the introduction with the cosmic tensions, here's how the constraints that we get from SIMBIG compares to the standard analyses for S8 and H0. So you can see that with SIMBIG, we improve S8 by nearly a factor of 2 and H0 by over 50%. So one thing I want to really emphasize here is that this is not a proof of concept applied only to simulations or to some idealized data set. This is applied to actual galaxy observations. So this is really a production level cosmological analysis. The other thing I want to emphasize to the non-cosmologists in the room who are maybe thinking, a factor of 2, who cares, is that this is equivalent to analyzing a survey with 4 times the volume with the standard analyses. So this is a really, really significant improvement. So to put it another way, the entire budget of BOSS was $15 million. So SIMBIG is worth $60 million. But of course, it costs much, much less than that. So really, again, that's obviously a joke, but this is just to emphasize that this is a really, really significant improvement over the standard analyses. So these are figures that you might be familiar with if you've looked at some of these cosmic tension papers. But here's how our S8 constraints compare with other cosmological probes. And the main point here is that we're only using 10% of the Boss volume, yet we're able to derive competitive constraints with other cosmological probes for S8. And similarly for H0, we also derive competitive constraints with other cosmological probes. Now, as exciting as all of this additional cosmological information is, everything that I've showed you so far is only with around 100,000 galaxies at around redshift of 0.5. So we're still not probing that regime that I mentioned earlier, where we currently do not have precise constraints on S8 and H0. But we're at a really exciting time because we have a number of upcoming galaxy surveys that will observe many more galaxies and really fill that regime. And in particular, we have the Dark Energy Spectroscopic Instrument, DESI, which is currently observing on the 4-meter Mayall telescope at Kitt Peak National Observatory. It finished its 3 years of observing out of the 5. And I showed you earlier the focal plane of SDSS with the manually plugged fibers. Well, the focal plane of DESI is filled with robotic fiber positioners and 5,000 of them that can simultaneously measure the spectra of 5,000 different objects across the optical range with medium resolution. And so with this instrument, DESI over the next 2 years, will finish observing. Oh, actually, I have another video. Cool. Well, these are the robots in action. You can see them moving. So they position the fibers in the exact positions of the galaxies. Now, you might be wondering, does this solve the fiber collision problem? And the answer is no, it actually makes it worse. But I can talk more about that if anyone's interested. So with this instrument, DESI will observe over 40 million galaxies all the way out to redshift of 2. And in particular, the sample that I'm very excited about is the DESI Bright Galaxy Survey, or BGS, which I've led for 3 years. And this will observe over 15 million galaxies during the dark energy dominated epoch. And so it'll observe during bright time. It's the first extragalactic survey to observe in bright time. But we scaled the exposures dynamically in order to achieve over 95% redshift success rate and with 99.5% redshift purity. And it'll produce a magnitude limited sample down to R of 19.5 and a fainter one across 14,000 square degree footprint. And so for those of you who are familiar with the SDSS main galaxy sample, this is 2 magnitudes deeper than that. And the reason why this will be a really exciting cosmological sample is that it'll provide a very high density galaxy sample that's more than an order of magnitude larger than any previous survey. So I'm showing you here the average number density as a function of redshift. I've plotted here SDSS main galaxy sample and the gamma DR4. And here's where the DESI BGS lies. So you can see throughout the entire redshift range of BGS, it'll have significantly higher number density. So what that means is that with higher number density, because that roughly determines the signal to noise of higher order statistics, we can actually expect the improvements from SIMBIG to be even larger. The other survey that I'm excited about is the Sumire Prime Focus Spectrograph, or PFS. And the Cosmology survey will observe on the 8.2 meter Subaru telescope in Mauna Kea. So I think starting next year. And it uses a similar robotic fiber positioner technology that's capable of observing 2,400 spectra simultaneously. And it'll observe over an even broader wavelength range, more into the IR, with a similar resolution. And because of this broader wavelength range, we'll be able to observe emission line galaxies to even higher redshift, all the way up to redshift of 2.4. So again, this is significantly deeper than the DESI sample. And so right now I'm working with Yuka Yamada, who's a graduate student at University of Tokyo, and finalizing the target selection for the PFS Cosmology survey. All right, so here's the figure that I showed earlier highlighting this regime where we currently do not have precise constraints on S8 and H0. And here's the constraints that we'll be able to get by applying SIMBIG to both DESI and PFS. And so as you can see with these new surveys, we'll probe this new regime of billions of years and really bridge the measurements of these parameters from the early universe, from experiments that probe the early universe to the experiments that probe the late universe. And more importantly, by extracting all of the additional information in higher order statistics and nonlinear scales, we'll really have the precision to distinguish, to really test these cosmic tensions and either confirm or resolve the tensions within the next couple of years. And so this will really enable us, forget about that slide, to test new physics beyond Lambda-CDM across cosmic history. So just, I think I have a couple minutes left. In the last few minutes left, I want to talk about how, we still haven't fully exploited cosmological surveys, even with the higher order statistics and the nonlinear scales. And that's because galaxies are not point particles. So I imagine at the IAC, I'm preaching to the choir here, but in addition to the positions and the redshifts of galaxies, these surveys will also measure their detailed photometry and also their spectra. And the photometry and the spectra, they include tremendous amount of information about the star formation history, the chemical enrichment history, and the dust content of galaxies. And by performing SED modeling, so modeling their spectral energy distribution, we can actually infer some of these properties from the observations that we have. So what that means is that with DESI and PFS, we'll have access to the physical properties of over 50 million galaxies. Now, whenever you scale anything to millions of galaxies, one of the challenges that we face is that, for instance, the standard Bayesian SED modeling, which is the sort of the gold standard of how we derive physical properties from galaxies, they take hundreds of hours, CPU hours per galaxy. And this is because you have to sample the posterior of a high dimensional parameter space. So even if your model is fast, it takes a long time. However, this is an easy problem to solve with machine learning. So for instance, I developed ProbablyGS with James Kwan, who's a graduate student at UC Santa Barbara, which uses neural emulation to speed up this process. So it only takes a couple minutes per galaxy to get full posteriors of galaxy properties. More recently, I developed SED flow, which uses a very similar normalizing flow setup, but it's amortized. So you only have to train the normalizing flow one time. And then afterwards, it takes 1 second per galaxy. Actually, I think it's much less, but I was using it slow. It was on a CPU. Anyway, it takes less than 1 second per galaxy. And so with these methods, we'll really be able to scale up these SED modeling and derive full posteriors of galaxy properties for all of the millions of DESI and PFS galaxies that we observe. So I'm going to talk about the galaxy evolution impact of what we can do with that tomorrow in the galaxy talk. But so I want to stick with the cosmology that we can do with this. So some of you may be familiar with this paper by Paco Villascusa Navarro back in 2002, Cosmology with a Single Galaxy. This was a rather controversial paper, but a really interesting paper that demonstrated that the physical properties of galaxies encodes information about cosmological information. Now, in practice, the physical properties of galaxies are not directly observable, so we don't have stellar mass or anything, but we can derive them using the actual observations that we have. So for instance, if we have some type of forward model that takes the cosmological parameters, the baryonic physics parameters, we can plug that into a galaxy formation model to predict the physical properties of galaxies, and then we can forward model the actual observations of, let's say, optical photometry. So if we have a forward model that does this, then we can actually solve the inverse problem because the galaxy formation model is basically a probability distribution of galaxy properties given the cosmological and baryonic parameters. And the forward model here is the probability of the observables, so the galaxy photometry given the physical properties of galaxies. So then we can rewrite a posterior of the cosmological parameters given the photometry here as this equation. So now, while the information is very, very limited for a single galaxy, once you actually go into observation space, what we can do is we can combine the information of many, many, many galaxies in order to place actually interesting constraints on cosmological parameters. So this is what I'm showing you here. This is from a recent paper that I wrote, where we combined the cosmological information from optical photometry alone of 20,000 galaxies from SDSS. And this is the constraints that we get on omega matter and sigma 8. And for comparison, I've included here the DES year 3 cosmic shear analysis. And you can see we're actually able to get competitive constraints as DES. Of course, there's a lot of assumptions that go in here. We use the illustrious TNG galaxy formation model, which we know does not reproduce all of the observations. And we made a number of assumptions, the SCD modeling. So all of those will have to be relaxed. But I think this is still a very promising approach because I only use 20,000 galaxies. And with DESI and PFS, we'll have access to 15 million galaxies in the future. So hopefully in this talk, I've convinced you that with galaxy surveys, there's a tremendous amount of both cosmological and astrophysical information that's available in galaxy surveys that we can use to settle the cosmic tension and really test new physics beyond Lambda-CDM, and also characterize how galaxies evolve across cosmic history. So I'll leave the, I don't know why this slide is here. Oh, well, and everything that I've talked about is still just the tip of the iceberg because I've only discussed DESI and PFS. And in the next coming decade, we'll have Rubin, we'll have Roman, we'll have DESI 2, Megamapper, Ultimate, Subaru. All of these new surveys will observe even larger cosmic volumes and probe even more galaxies. Right? Oh yeah, and Euclid. Yeah, Euclid should be there. So I'll leave my summary up here, and I'm happy to take any questions. Thank you.
Thank you very much. Very nice talk. So, okay, see, first question.
Thank you. So at the beginning of your talk, you showed how much information content you could access with these methods, with machine learning based on the different, I think, power spectrum combined with bispectrum. And it seemed to saturate at about K 0.5. And I guess that's the reason why you stopped at that K to. And my question is, it seems to flatten, right? And my question is, why do you think is that the case? You're using in an indirect way. I mean, you're doing it at the field level, but there is information on the baryon acoustic oscillations. There's information on the redshift space distortions as you're accessing also multipoles. Have you tried to, have you made comparisons? How much information do I access if I do the analysis in real space and not in redshift space? And if I do big simulations without the baryon acoustic oscillations imprinted in the initial conditions, for instance, to see I'm curious about where that information is.
Yeah, I mean, so that's an excellent question. And we've done some of the tests that you've talked about. We haven't really done an exhaustive search through all of these, unfortunately. But in terms of why there's a saturation of information, it's one of the main driving factors of that is that we're using a bias model. So we include an HRD model in this forecast. So once you marginalize over those parameters, then the information does saturate at some K value. And so what we find is that with the bispectrum, once you add that, you're able to break some of the degeneracies with the HRD parameters, and that allows you to the improvement to continue down to smaller scales. But eventually you also reach some degeneracy. And in terms of, is this why we set the scale limit of K max of 0.5 in our analysis? Well, it was mainly driven by the fact that even though we used the Kyoto high resolution simulations, we only trusted it up to K of 1. And then there's also these questions of the effect of baryonification and baryons. And so based on previous studies, we found some works that showed a 1% effect at K of 1. So to be conservative, we selected a K max of 0.5. So it wasn't necessarily based on the saturation, because it would have, I think, independent of that, we would have liked to see whether we hit that sort of saturation in the actual analysis as well. So it was mainly driven by the simulation accuracy that we were concerned about.
Thanks so much for a very nice talk. Connecting to Paco's question, I understood that you are learning from a pool of models of simulations, right? My first naive question would be, can you, in this pool of initial simulations from which we are learning, be sure that you're actually probing all baryonic physics that could actually be impacting your observables? I mean, is there a systematic way to actually sample all possible baryonic physics?
That's an excellent question. So I can tell you more broadly about some of the tests that we ran to convince ourselves about the robustness of our cosmological parameter constraints. So in addition to the 20,000 simulations that we used for the training, we also constructed these 2,000 additional simulations that were constructed using 3 different forward models. So the first one, test 0, is with this fiducial model that we use. With test 1, we vary the halo finder. We also vary the HOD model. And then with the last one, we vary the M-body simulation, the halo finder, and that's actually not correct, but we also vary the HOD parameters. Mm-hmm. So what we do is we construct these 2,000 independent test simulations. And then for each one, we treat them exactly like the observations, except we know the true cosmological parameters in this case. Mm-hmm. So we run it through the entire SIMBIG pipeline. We compare the inferred posterior of omega matter and sigma 8 here, for instance, to the truth. And because we have 2,000 of these, we can do this on each and every single one and confirm whether statistically we're able to reproduce the true posterior of the cosmological parameters. Mm-hmm. And so only after we've done this test do we actually apply them to the observations. Mm-hmm. So now this doesn't fully answer your question of do we explore the full space of baryonic physics, and that actually points to what we're working on next, which is here. We're trying to, we're calling it SIMBIGger, which is trying to better model the galaxy halo connections by learning from hydrodynamical simulations. So I don't know if you're familiar with the CAMELS suite, but these are for the rest of the audience. These are hydrodynamical simulations run at different cosmologies and different values of the hydrodynamical parameters. And so what we can do is we can actually learn the galaxy halo connection from these simulations, and then use that either as a test simulation or to learn the functional form of the HOD to then populate our training galaxies. So that's what we're working on right now. And so these figures that I'm showing you here is made by James Kwan. They're showing you the distribution of the kinematics of central and satellite galaxies with respect to the halo center for different values of the baryonic physics parameters. And interestingly, we actually find almost no effect of supernova or AGN feedbacks on the kinematics of satellite and central galaxies for luminous red galaxies, for instance.
And the second part of the question, maybe it's my ignorance. I've seen that this active field theory has been applied on standard BOS, EBOS surveys, and they've been reanalyzed and so on. I missed this technique being applied on the standard BOS, EBOS data analysis. Did I just miss it, or are they out? Have you already applied this methodology on the standard catalogs from CMAS, LUCI, for the full cosmological analysis of those galaxy surveys?
Sorry, which analysis are you referring to? Symbiotic
just
analysis?
analyze, yeah, no, the standard analysis, just analyzing the standard BOSS Galaxy spectroscopic catalogs and the eBOSS, both Galaxy and Quasar catalogs. Have they been analyzed with your machinery?
So the results that I showed you were with the standard BOSS.
Standard BOSS.
Yeah.
Okay.
So the CMAS sample is the standard BOSS,
Okay.
luminous red galaxy sample. Sorry, I should have mentioned that. We haven't applied this to eBOSS yet because, well, I'm heavily involved in DESI. So
You're busy.
also, why would we analyze yesterday's data when we have tomorrow's data already? So we're focusing on extending this to DESI year 3.
Thank you.
Okay, hello, thank you for your talk. I was curious about, at the beginning, you mentioned that when using normalizing flows, one of the input was the summary statistics. I mean, you first need to compute the power spectrum, bias spectrum, Minkowski coefficients, and so on. But this is also, I mean, my question is, why not to extract directly those features, the statistics, with the normalizing flows instead of passing it as an input?
That's an excellent question. And this is actually what we're trying to do with the convolutional neural network compression of the galaxy field. So I think it's a really, really good question of, we have all of these methods with machine learning for extracting relevant information. Do we even need summary statistics? And I think when I started the project, I was very much like, summary statistics analyses, there's like a 2-year lifespan. Now that I'm developing this, no one's going to look at summary statistics anymore. But I'm actually not convinced that summary statistics should go away. Because one of the problems that we faced when we were training the convolutional neural network is that it was really, really easy to overtrain and overfit the model, the CNN, meaning that the CNN quickly picked up on very model-specific features in the galaxy clustering. So when we applied them to the test simulations, they produced biased cosmological constraints. And so with summary statistics, you can be you have more intuition about what they should actually look like. The exact cosmological features in the bispectrum have been studied, by Roman since the 90s. And so that is super helpful. And you can also do very clean scale cuts. And that sort of intuition, I think, is really, really important for deriving robust cosmological constraints. So in the case of the CNN, we have to do a lot of regularization and all of these things in order to improve the robustness. So in that way, coming up with newer summary statistics that are more informative, that's sort of a solved problem. It's more about coming up with summary statistics that are informative of the cosmological parameters, but are agnostic to whatever modeling limitations that we have. I think that's the new challenge. And we're also working on ways of doing that where, for instance, you can imagine training a CNN, but with multiple different forward models, and then you penalize it every time it's able to guess which model it's constructed from. So you're forcing the network to just not learn anything that's model specific. But yeah, I think that's really where the next step is going to be.
Okay, thank you. Sorry, another question. I mean, for analysis beyond Lambda-CDM, let's say modified gravity, is there some progress in that direction?
Yeah, well, so the next sim bigger that we're doing is actually going to include neutrinos, and it'll be neutrino W Lambda-CDM. I think we're also interested in doing primordial non-Gaussianity as well. But at the moment, we're person power limited. So if you're interested, we are an open collaboration.
Okay, then we can finish and thank again.